Hey, my name is Eva, and this is Blond Quantum, the podcast that breaks down quantum technology into real-world business impact. Here, we make the complex simple. No equation, no overthinking. Just insight, innovation, and a bit of humor. So don't worry, you don't need a PhD in physics to follow. In each episode, I talk to founders, scientists, and investors about how quantum is reshaping the industries today, not in some distant future. Oh, and if you hear a black cat purring in the background, that's my co-host, very alive Schrodinger's cat, joining the conversation. Her name is Moon. Let's get started. Hello, everyone. Welcome to the next episode of Blond Quantum. Today, we have a very unique episode. And I know I will usually say that every single episode because for them, all of them are unique. But today, we do not have any average startup success story. We do not have an enterprise story. We have something different. In the world of startups, if you fail, you usually raise again. Many founders doing 2 or 3 startups, they raise more money. In physics, if you fail, that's a different story. The academia may shut the door forever. That's why it's important to ask the big question. In early 1980s, a young, ambitious French researcher decided to take the bet anyway on the question that even Einstein was considering to be already settled. And he won. He won the Nobel Prize in Physics in 2022 for proving that entanglement is real. The physics phenomenon that is behind and shaping today reality of quantum computing, quantum sensing, quantum all information. Please join me to welcoming the man that proved Einstein wrong, the professor of the Optic Institute on Paris-Saclay, professor of École Polytechnique, and a co-founder of Pasqal, Professor Alain Aspect. Hello, Professor.
Hello.
Thank you so much for joining me today. It's a big, big honor for me.
Well, it will be a pleasure to try to explain a little bit about quantum physics.
Yes, today is a little bit different because I bet usually you address more academia, more investor audience. Today we have an audience who are really only business. So we cannot use the industry lingo. We need to explain even the simplest theory in practice. But before we go through all the details of physics, of your experiment and so on, I want to start with your story. In 1980, early on, when you started proving the Bell inequalities, many people were considering this to being much closer to philosophy, I guess, than the real physics. So my question is, what make you bet on that specific field?
Okay, first, let me make it clear. It was yet earlier. It was in 74, 75. I read the paper of John Bell showing that there was a phenomena, entanglement, on which Einstein and Bohr had debated. They had opposite point of view, and Bell showed that this opposite point of view, apparently philosophical, at the end of the day, you could settle the debate with an experiment. I thought it was the most interesting subject I had ever heard of, so I decided I wanted to work on that.
And at that time, I have heard you saying in some other interviews that many physicists and researchers, even those who you deeply admire and respected, were discouraging you to do that. And they were specifically saying that it may hurt your future career. So did you really consider that?
Oh, of course, I heard these people telling me that quantum physics has been demonstrated good in so many experiments that the debate between Einstein and Bohr had been settled for a long time. And I love looking into history of physics, and looking carefully into the history, I found that they were not right, that there was a first debate in 1927 which had been settled at the advantage of Bohr, but the second debate in 1935, the famous Einstein-Podolsky-Rosen paper and the debate about entanglement, I found that this debate had not been settled, and there was a way to settle it. So when people told me that it would hurt my career, they were probably true, but due to a specific system in France, I had a small but tenured position. So I decided that I could take the risk to remain a low-level teacher at university, provided that I could do what I like. And so this is how I embarked into it. But to make the bridge to the years 81 and 82, when I obtained the result for my experiment, I think that something very important happened. I found clear, simple way of explaining why the problem was interesting. To make a long story short, when a colleague was telling me, but look, you are wasting your time. You know, this subject has no interest. I would tell, do you give me 15 minutes? And in 15 minutes, I was able to explain why Bell theorem, Bell's inequality testing was interesting. And then the colleague would tell me, but this is interesting. I say, yes, it's exactly why I'm doing it. And so when I defended my PhD thesis in 1983, the auditorium was full. There were people out of the auditorium who could not enter. So in less than 1 decade, I had been able to convince many people that the subject was interesting.
And the whole community. And is it true that your thesis advisor, when you picked the thesis as part of your PhD, he advised you to go to Geneva to meet John Bell himself?
Absolutely.
Can you tell us a little bit about it?
Well, yes, my thesis advisor was a very young and energetic optics person, but he did not know about quantum physics. So when I came, but he liked risky experiments, okay? And so when I told him, look, this is what I would like to do, he said, okay, it seems really interesting, but I don't know enough of quantum physics. Go to Geneva, talk to John Bell, and if John Bell tells you that the experiment is interesting, then you can do it in my laboratory.
And is it true that John Bell asked you if you, the first question he asked you was if you have a permanent position?
Exactly. So, because of what we already discussed, John Bell knew that it would definitely hurt the career. But when I told him, look, I have a permanent position, then we started talking physics, and then he encouraged me and told me that my experiment was really interesting. And moreover, you know, I already had the idea, which was an idea for switching. Maybe we'll talk about that later. But I thought it was an original idea. And I asked him if he would recommend to keep it secret or to publish it. And he said, we are talking about the basic research. You better publish it. So I published it. And it turned out to be very important because I think that 40 years later, when the Nobel Committee was looking at what I had doing, there was a proof that it was my idea because I had published it early enough that it was clearly my idea.
So that's the first lesson for a young researcher. Always publish.
Absolutely.
Absolutely.
Absolutely. The question is different for some technological advance. Okay, you are in a lab, you have a problem, you find a trick to overcome the problem. Basically, you don't publish it, okay? But when it is an original idea, innovative idea, you better publish it. Just to show, because it's very likely that some other person will have a similar idea, and if you have not published, then it will look like you you stole it from another person. So it's better to publish when you have an idea which seems really original.
And that's proof, right. So let's talk about the switching point, because what you did actually was the switching experiment, and this switch the measurement when the photons were on the movement, from my understanding. So can you tell us a little bit more where the idea come from to you? Was John Bell also involved in it, in helping you or advising you on it? Or was like on your own with this? Tell us more about it, please.
No, John Bell was absolutely not involved in any idea about experiment. My guess is that even if he had opinions about experiment, he would not say it. He considered he was a theorist, his business was theory, and my business was experiment, and so he did not interfere.
So out of respect to you and your experiment, he would not?
Yeah, I think it was his attitude towards experimentalists insert, the big accelerator. He did not want to interfere with the experiments. No, well, the idea of the switching needed, well, first, maybe we should start by describing the experiment anyway. So I have a source emitting two photons. One goes on the left at 6 meters, the other one goes to the right at 6 meters, and I make measurement with a polarizer. Polarizer is an apparatus of which you can change the orientation, and once it is in one orientation, when the photon arrives, you can get two possible results that we label +1, -1. It's arbitrary, but let us say. And the idea of the measurement is to measure the probability to get +1 and -1 as a function of the orientation of the polarizer. And the idea of the final experiment, the one which was really original, suggested by John Bell, was that it would be a good idea to change the orientation of the polarizer while the photon was flying from the source to the polarizer. It takes 20 nanoseconds, 20 billionth of a second, which is very fast. So there is no question of really turning an apparatus. And so I began to consider many possibilities. And finally, I say, if I could build a switch able either to let light go straight or deflect light at an angle, and if I was putting one polarizer at an angle in the straight line and another polarizer at another angle, if the switch was fast enough, it was clearly equivalent to a single polarizer switching from first orientation to second one, to the first, to the second one. So the point was to develop a switch. And then the idea emerged from, I would say, the conjunction of two things. First, I was teaching with very smart students, and they had a debate, a strong debate, which was really interesting, about diffraction of light by acoustic waves. And, well, technically, the discussion was, is the diffraction phenomena different when you have standing waves or running waves? And so they were debating between them, and I thought as a teacher it was my duty to think about it and come with an answer. And then I realized at that point that, yes, it was different, and that with a standing wave, I had probably a way to build the switch. So, I'm very glad because I love teaching, and I think that this idea, which is crucial in my experiment, came because I was teaching and that I was taking seriously my duty of thinking about the question of the students. Well, I can add that, in fact, at that very moment, so I found that a stationary wave was the solution. And then I thought about an experiment done by my high school teacher to show exactly the evolution of a standing wave. So in fact, I put two things together, the fact that I was a teacher and the fact that I had a wonderful teacher who had shown me the details of this kind of thing. So it's kind of...
That's fascinating. And so the switch was the reason why the other experiments on the Bell inequalities were not successful?
No. The switch was, so to speak, the cherry on the cake. The first experiments were experiments in which the polarizer were static, and already these experiments are very important. The first one was done by John Clauser in 1972. And these experiments are quite interesting, and getting the result of this experiment really says something. However, you can still pretend that there is some possibility that both ends of the experiment communicate by some unknown interaction. That was the idea of Bell. And so Bell has said, ideally, you should change the orientation of the polarizer while the photons are in flight, and then you prevent any communication between both ends of the experiment unless that communication is faster than light. But, it was another experiment. It was, well, as I say, it's more than it's a big cherry on the cake. But the first experiment by themselves were already beautiful tests of quantum physics. People have the idea that there is one experiment that decides, but it's not like that. You start with an experiment which is far from perfect, then the next one is a little more sophisticated, then you have another one better. And of course, the scheme with the switches was a different scheme. But my experiment with the switch was really far from ideal. But it took another 16 years until somebody repeated it. And then when that person, Anton Zeilinger and Greg Weiss, repeated that experiment, it was, of course, much better than mine.
Well, after 16 years,
yes. Exactly.
Yes.
So that's the way experimental physics is progressing. But before that, we had done 2 experiments which were more or less repeating the previous one, but with significant improvements. And everything started from the fact that I took several years to develop a totally new source of entangled photon. This was the key. In physics, you want to have a good signal. Yep. And so I was working on photons, and I wanted to have a good source of entangled photon. It took me several years to develop that source.
That's very interesting, actually. And it is, in fact, a little bit similar to the startups. The signal is the market research that the startup are doing. And the next research that you do, the next reputation is like the iteration in startups. So I'm glad to see that. And hopefully we come back to this topic as well, because you're also a co-founder. So we will come back to this topic. But I wanted to ask you right now something else. And before I ask you that, I would like you to explain what are the local hidden variables, because that is necessary for the next question.
Okay.
And I'm afraid our audience may not.
To take a few minutes. The idea is the following. So I have 2 photons, I have 2 measuring apparatus, and on each measuring apparatus, I can, for a given orientation of the polarizer, I can get either a result +1 or a result -1. In the situation that we consider, the probability to get +1 and -1 are equal, and it looks totally random. So on one side, it looks totally random. On the other side, it looks totally random. But if you watch simultaneously at both sides, then you find something strange. Although it looks random, if you get +1 on one side, you get +1 on the other side. And if you get -1 on one side, you get -1 on the other side. And then how can that be? In fact, there is an idea which is quite simple. Because the 2 particles have been formed or emitted simultaneously in the same source, the most natural idea is that from the beginning, they carry along a hidden variable, which tells it will be +1, +1.
It's basically set a feature.
Yes. So why do they call it a hidden variable or supplementary parameters? Because in the formalism of quantum physics, all the pairs are described similarly by a mathematical object called a vector in a Hilbert space. Doesn't matter. They are all described by the same mathematical object, okay? Here, I'm pretending that some pairs are +1, +1 from the beginning. Other ones are -1, -1 from the beginning. So I add something. I add a supplementary variable. This was a debate. Einstein was very happy of that because Einstein thought that in order to really understand the random character of quantum physics, you need to introduce supplementary parameters. I like to make the following example. Here in this room, we have molecules of oxygen flying, okay? And we can describe the probability to have molecule with a certain velocity by a law, which is well known, a Gaussian known as a Maxwell-Boltzmann distribution. So statistically, we say the probability to have this velocity or that velocity has a certain value. But we have no doubt that each particle, in fact, has a given velocity. These are the supplementary parameters. So using probability is convenient because it makes the description easier from a mathematical point of view, but we think that there is something below. It seems that it was the idea of Einstein. Einstein thought that because the formalism of quantum physics gives probabilistic result, there should be an underlying level. In this example of entanglement, Einstein say, if you want to have a sensible image of what's happening, you have to accept that from the beginning they have this supplementary idea. This was a philosophical debate between him and Bohr because nobody could convince the other one. Einstein had his reasoning and Bohr was claiming, no, you don't need to do it. And okay, it looked totally philosophical until 30 years later, in 1964, John Bell discovered that if you take seriously the idea of Einstein, at one point, the level of correlation, that is to similarity between both sets, that you can predict with hidden variable theory is not as strong as what quantum physics predicts. So this doesn't happen often. Yeah. But if you build an experiment in such a situation where standard quantum mechanics and Einstein point of view give different prediction, you do the experiment and then you can settle the debate.
And that's what happened, right? When your results came on, they were matching the result of quantum mechanics rather than the local hidden variables. So I wanted to actually ask you, what was the reaction of the physics community? Because...
Well, as I told you, when I obtained this result, I have already convinced people that it was an interesting equation. But most of them had the prejudice that quantum mechanics was so successful, why would it fail here? And in fact, their prejudice turned out to be correct, but something had happened. When I started, people had not realized that the equation of entanglement was different in nature from what they had previously thought as Feynman say, the big mystery or the big feature of quantum physics, which is wave-particle duality, okay? I like to speak of two quantum revolutions. The first quantum revolution that emerged in the beginning of the 20th century and until the development of transistor, laser, etc., is based on the fact that a particle should, like an electron in a solid, should also from a certain point of view be considered as a wave, and vice versa, a light wave should, from a certain point of view, also be considered as made of particle, photons, okay? But all that was about individual particle. Maybe many individual, but many. An individual particle is also a wave, etc. Entanglement is really something different because it is about two particles, okay? And so from a mathematical point of view, it's totally different, but also from a point of view of the image you can make in our space. When you have a single particle, a particle has a trajectory. If you think of it about a wave, it is a wave in our space. Of course, it's strange that the same object can be both a wave and a particle, but at least I can think about it in our space. When you have two particles entangled, you cannot think about it in our space. You have to think about it in an abstract Hilbert space, which is really a space which has no direct correspondence to the space where we live. And so this tells you that entanglement is really something different. And progressively, people realized that entanglement being something really different, there should be different physics and different technology to be made with it. The best example is the famous physicist Richard Feynman. Almost everybody had heard of Feynman. In his famous book, Lectures on Physics, in the 60s, he addresses the question of the Einstein-Podolsky-Rosen equation. And he says explicitly, when you look at it from the same point of view as wave-particle duality, you find that there is no problem. Okay? 20 years later, in 82, he writes a paper where he says, maybe entanglement is more subtle than I thought, but Feynman being Feynman, in the same paper, immediately, he begins to elaborate on the first ideas about quantum computing. So he realized that entanglement is different, and then there is new quantum technologies ahead. And so I think that when I defended my thesis, many people were interested, first because the settling a debate between Bohr and Einstein was interesting, but many people at that point realized that it showed that entanglement is definitely different.
I see. And you just mentioned that. So I think there was a period between 1930 to 1960s when literally these problems and the fundamentals were not addressed. Do you think if the physicists were paying more attention at the time, then we would have this quantum revolution, information revolution much faster than?
I am not sure. I believe that science evolves as, for instance, Thomas Kuhn says, that is to say, you have a phase where you work on a well-established theory and you push that theory as far as you can. And I think ideas have to mature, okay?
I like that.
What happened between the 30 and the 60 is that any problem to which you would apply quantum physics could be solved with quantum physics. So look, you are an active physicist, you use quantum physics, it works. You have heard that there is a philosophical debate, okay? It's only philosophical between Einstein and Bohr. You say, okay, when I have time, I will think about it. Maybe when I retire, I will have time to think about it. So I think you need to have things to mature. Moreover, there were people who had begun to think about it, Bohm and Aronoff in the 60s. And they had realized that some experiments may tell something about the debate, but in fact, technology was far from being mature to be able to test the experiment. It turned out that optical photons were the key for it, and really it demanded the technology which were developed only in the late 60s or in the 70s, etc. For instance, in my experiment, the efficiency of the source of entangled photon was based on the use of lasers which had just been developed, and moreover using a process known as a two-photon excitation, demonstrated just 1 year before, So
it wouldn't be possible before.
Yes. So, even in your interest in industry and startup and things like that, my experience is that it's not enough to dump money to obtain a result. This is why, maybe we talk about that later, this is why I'm such an enthusiastic person about the close link between academic research and startup and keeping this link. And at each moment, the academic research provides new ideas, and then the startup is here to realize them from an efficient technical point of view. You cannot really accelerate basic ideas just by dumping money on it. Well, of course, if your money is used to hire people who think about it, helps. But, ideas have to progress step by step.
And we need the maturity. That's actually very interesting, and I think it's a very important lesson as well for both the startuppers, the entrepreneurs, but also for the investor. And I will pick you on this as well. But before I do...
Yes, I would be happy to speak about that, because I'm proud that France, really from this point of view, has taken the lesson from what happens in, I would say, Harvard, Stanford, MIT, where indeed many startup companies start from an academic lab. Then there is a young guy who starts the company, but very close to the lab. So there is constant exchange, and
feedback.
And the professor is an advisor, etc. This is exactly what we have done with Pasqal, which started in my institute, Institut Optique. They had space to start. Every day they were talking to the people of the academic lab from where the idea was coming. And now they are bigger, but they are very close, and there are still discussion on a weekly basis, etc.
So let's talk about it. Once you started, because that's a very interesting angle as well, and you obviously were a co-founder of Pasqal.
Yes.
As you said, it started in your institute with your colleagues and ex-employees. And right now, Pasqal is obviously preparing themselves to going IPO shortly.
Yes.
What was the point when you were still in the lab, in the institute, and you realized, we are getting to the point when these may actually have market and commercial readiness and importance to create a company from that research?
It's not at all me. When I finished my experiment, completed my experiment in 82 and defended my thesis in 83, I really thought that it was the end of a story. I had settled a debate between Bohr and Einstein, which is not bad, okay? And then...
For 35 years old?
Yeah,
How old you were
yes.
at that time? Something
So,
like that. Yeah,
and
not
then
bad.
I was attracted by Claude Cohen-Tanucci, who wanted to develop a new program about manipulating and cooling atoms with lasers. And I joined him. And just to make a long story short, we were successful enough that he got the Nobel Prize in 97. Okay?
Great.
And I was a member of that team, and I did put my stone on that, okay? Yeah. And so I was totally involved in that new subject of research. I thought it was totally finished. But then I began to hear about people saying, we can have interesting application of entanglement. For instance, one of the first was Arthur Eckert, who invented a method of quantum cryptography based on entangled photon. And this young guy, maybe he had not yet defended his PhD, came to me and said, Professor Aspect, that with your entangled photon, we can do quantum cryptography. I said, what? Okay. And then I began to be interested more and more in that, but did not return. Okay. After I was still working with ultra-cold atom, Bose-Einstein condensation, etc. But I was talking with people in my institute, and one of my former PhD students, Antoine Broes, who is a fantastic scientist, he is collecting international prizes, etc., and he started to think about using entanglement of neutral atoms for going towards quantum computing. And so it was still an academic experiment, but, I had close contact with him because he was my former student and we had a nice discussion together. And one day he came and said, look, there is a guy who came and he tells me that we should do a startup.
That was Christophe.
And that was Christophe Schurzac. And I say, what do you think, Antoine? And so Antoine say, he says this and that. And I say, what do you think? He tell me, I think it's reasonable. So I say, if you think it's reasonable, go.
Go for it. Do it.
Go for it. And he say, I will go only if you come with me.
Oh,
this is why I am. This is how I am involved, and I'm very happy because I still help him to keep the point of view of the academic researcher, and I think that this is a beautiful feature of Pasqal, that we have people who really know business, know technology, know 100%. Engineering, etc. But Antoine is still having his basic research lab, and he's happy to discuss with me. And so...
And many think that Antoine is actually following your steps. And
well, maybe.
We'll see. We hope for it. But yeah, definitely. And that's make Pasqal also unique in the case that they are probably the only neutral atom computer company who are having a Nobel Prize winner.
Yes, but look, the competition which is in Harvard has Misha Lukin, who is in it.
True.
And, Misha
They're
Lukin
also very strong.
has not a Nobel Prize, but maybe he gets one. And he's really a star in the academic world. So, no, I think in a sense it's similar.
So there's two companies.
It's a real competition.
Yeah, it's a real competition. That's good. That's good.
Absolutely.
That's definitely keep everyone on track and speed up things.
Absolutely. I think competition is good.
Healthy competition is important. Yeah.
There is another competition. Maybe you have not planned this question, but there is another competition which I like very much, which is competition between quantum computing and pushing classical computing. Take the example of a calculation that Antoine Broes has done, which is about a problem which has been known for decades, known as the Ising problem. You have many particles with a spin, and you look for what we call the fundamental state of the system, the state with the lowest energy. You cannot solve that problem on a classical computer by brute force, that is to say, starting from the basic equations for more than, I don't know, let's say 80, maybe 90 particles, okay? Antoine Broes solved it for 250 particles, okay?
Wow.
So this is real quantum advantage.
Yeah.
Let me make a comment. When people claim quantum advantage, look at the problem they are solving. If the problem has just been invented to show that they have quantum advantage, is not so interesting as if it is a problem which was already there. And the easing problem that Antoine is solving was in the book of condensed matter physics for decades, okay? Amazing. So it's a real problem. So he solves it better than a classical computer. But of course, people of classical computing are smart people. And so they develop approximation method, which allow them to calculate with 250 particles. But they are not true, because when you have an approximation, it may be wrong, okay? And so it's a very nice competition, because at the end of the day, Broes and the people of the approximation in quantum computing can compare their results, and they find the same result. So they are all cross-checking each other. Yeah. I think this kind of competition is really good science, excellent science. Yeah,
that's amazing. Speaking of, because you mentioned that, a lot of the entrepreneurs who are now starting quantum startups, they came already after the transformation, as we can call it. Do you think any difference between how your generation, how people were asking the fundamental questions to solve or problems to solve, and those people today who are having a little bit different reality, because a lot of these fundamental questions, where are the answer, or they are established, there are some fundamentals they can work on and build on?
No, I don't think that it is fundamentally different. When people invented laser, it was first a fantastic toy for physicists. The light emitted by laser had properties absolutely extraordinary. And then progressively, people began to think it could be applied for this, for that. But at the beginning, it was really a beautiful tool for basic physics. So I don't think that it has changed. In France, what has changed, as I told you, is the fact that in the last 2 decades, now we have no problem of saying an academic lab can have a spin-off, which is a startup, etc., etc. It was not at all the case when I was a student. When I was a student, if you would go for application, it was just getting your hands dirty, okay? And so you had to choose. Either you go to get your hands dirty, but if you are a serious researcher, you don't do that. Now it's totally the opposite for many reasons. The French government, along the various French governments for the last 2 decades, I would say, have really done a lot of evolution about that. They give funding for the initial step of startups, etc., etc. And on the other side, the university people and the academic people have realized that having a good industry is important.
It's important, yes. Actually, I would love to talk a little bit more about it, because France indeed is very unique in terms of, if we look in a European scene, in terms of like how the government supporting the local national startups. And I had a chance to speak with a couple of people in UK, in Germany as well, and in France, obviously. And what I think is very unique as well, that here government in France are also investing in the startups directly or semi-directly. They invested in Pasqal, they invested in Bobenalis and many others.
In Candela, which is with photon, yes.
Exactly. So do you think this is the recipe for success? Or what changed those 2 decades ago when they decided, okay, we want to build another big industry, and we're going to support those startups, those researchers, those institutes, and so on?
Well, I think it's a good idea. I don't know if it is a recipe for success, but if you don't do it, it's a recipe to have no success.
That's true.
No, I'm very pleased by that, because once again, we have to realize that having a good industry is very good for basic research, because first they pay taxes, but also because they develop technologies which are close to you. What I have found, I'm an experimentalist and I've used sophisticated technologies. And what I have always found is that when there is a French company close to me which master that technology, is extremely useful, because if I have a problem, I can just go there. It takes me 1 hour and discuss with them. They will help me, etc. So I think it's good for basic research to have a good industry which is developing reliable technology. Basically, the technology that we develop in a lab is not reliable because we are just at the cutting edge, and as soon as it works a little, we try to find something new, okay? while industry has to make that reliable. And that's the idea of Pascal. Pascal is making reliable the machine of Antoine Broes, and Antoine Broes is making discoveries, world premiere, but this machine works from time to time, and then he gets a wonderful result. And the job of Pascal is taking a similar scheme and build a reliable machine.
Fantastic. So here is another lesson, guys. Close cooperation between labs and academia.
Absolutely.
And the industry as well.
Yes.
Okay. Professor, I would like to a little bit maybe change the topic and talk about the market expectation, however it sounds. So, since the moment when you perform your experiment in early 80s to the moment when you were awarded, it took 4 decades.
Yes.
It's a really, really long time.
Yes.
And I'm under this impression that in academia, that's in sense normal, and that some things need to settle, some things have to mature, as you said. Now, when we look at the startup industry, both entrepreneurs and venture capitalists who are obviously investing them, they're pushing for faster outcomes because they have to. I mean, investors are expecting the returns on the capital and so on and so on. Startups also have this time. What do you think? What's the lesson on this that both sides can learn from each other, and how to balance this commercial readiness with the need of developing deep technology that takes time?
I don't think you have to balance. You have to do everything.
You do both.
More. You have to really to continue do the academic basic research. You need in the startup to try to develop new technological solutions, patents, etc. And then you have to build machine that you can deliver and give to the customer with the solution you developed 1 year or 2 years ago. So I think I will speak of 3 different rate of processing. And I think that there is no other way of doing. But what I see is that really the fact that you promise a product to a consumer or to somebody who has bought the product forces you to be smart and to develop your technology maybe faster. But I did that for my thesis, because what happened for my thesis is that my idea of acoustic wave interacting with light, I went to a company building devices where you have interaction between acoustic wave and light, and they promised to build it. But when I needed it, they could not, because they had a technical problem. I think it's interesting because, in a way, the kind of problem that you can have in a startup. The problem that what I wanted was bigger than usual, and when they were trying to glue transducers on my big crystal, and they had to do it at hot temperature, when the temperature was decreasing, it was breaking. So there was a problem of different dilation between the transducer and the crystal. And, exactly like the startup company which has to deliver, I had to deliver. In a sense, I had to do my experiment. Everything was ready. And what does a physicist do when he has a problem? He looks carefully into the subject. So I began to read books of acousto-optic interaction. And in that book, to my surprise, I discovered that water was a good medium for acousto-optic interaction. And then immediately I say, there is no problem of dilation. I put my transducer in water and it will work. I did it and it worked. And I had this experience that you promise something and then you cannot deliver and you have to fight harder. You fight for your life.
Wow.
So,
that's very inspiring.
I'm not so surprised that sometimes in Pasqal, they say, hey, we have to deliver that. Okay, you have to find a solution.
Yeah, exactly. Wow. That's beautiful. That's very inspiring. Okay. I wanted to ask you as well, if you can explain the entanglement to the investor and entrepreneurs in the way that helps them understand what is realistic and what's not realistic in a quantum technology in the next decade. What would you say?
I don't know.
You don't know?
No,
okay.
I don't know. I think that it's a good idea that venture capital invest in quantum, knowing that venture capital does not always win. So I would never promise that it will win, but I fully disagree when some of my colleagues say it will never work. I think it's totally open. Well, if I would have to bet, I would bet 50%. Okay, chance that it works, which I think is okay for venture capital to have a return of 50%.
They have usually 20 bets. So.
I tend to be optimistic in the long term because it seems to me I am very interested in a history of science and technology. And according to many examples in history, when something is not forbidden by a fundamental physics law, sooner or later, engineers succeed. Well. And so it seems to me that there is no fundamental law saying that good, fault-tolerant quantum computer cannot exist. So I tend to think that it will eventually work. I don't know how long it will take. And maybe there is another possibility, which is exciting for a physicist, but not so much for investor. We might discover a fundamental law saying that it is not possible to have a quantum object bigger than, I don't know, 1 million qubits or something like that. We may find some fundamental limit of which we have no idea today. This would be fantastic for physics. Maybe investor would not appreciate, but I think the most likely is that it's only a matter of improving technology, but we need big improvement of the technology.
100%. Wow. So this is very interesting what you said, actually. So we shouldn't focus what's possible, what's not. We should focus on what's not possible, what the fundamental physics basically is.
Absolutely.
Yeah. Those are about everything else is possible.
There are things you should not do because you know that according to the laws of physics, it cannot work, period.
Yeah, that's it. Everything else is...
Well, when I say period, it's more subtle like that. We have some no-go theorem. So when you have a no-go theorem, you should not do what is in the hypothesis of no-go theorem. But maybe to obtain this goal, you may turn around, go around the difficulty. So a no-go, it happened to me in my career. There was a no-go theorem. You cannot do that. Okay, you cannot do that in this condition. So it tells you if you do it this way, it will not work. And I got an idea to get around the difficulty and obtain the result, although it sounds impossible. So no-go theorems are very interesting because they may suggest a way to get around.
Was that when you were working on holographics before?
No, it was when I was working on laser cooling of atoms, controlling the velocity of atoms as well as possible. One could demonstrate that you cannot cool it below a certain temperature, very low, nanokelvin, okay, very close to absolute zero, but it sounded to be an ultimate limit because it's a limit corresponding to the random emission of one photon. And when there is a random emission of one photon, there is a small recoil of the atom. It sounded to be impossible to control the velocity better than that. Being aware of that, I found a way to exploit that last recoil to go even lower.
Professor, when I listen to you...
This was my contribution to the Nobel Prize of Critical Intelligence.
Oh, beautiful. When I listen to you, I see still this enthusiasm on the... You're a real experimentalist.
Yes.
And that just actually reminds me...
Physicist. I love physics.
Yeah, I see that. I can see that. And that actually reminds me, I was about to ask you, because you had a period of your time, and you actually mentioned that you love teaching. I have read that your parents were also coming from a teaching background. And I read that you spent 3 years in Cameroon when you were far from experiments in the lab and far from the academia and mostly focusing on just teaching.
Absolutely.
Can you tell us a little bit more about that experience and what that teach you in the sense to, find your way? Because I understand that was in the beginning of your career. So there was the moment when you decided, okay, I can only teach. I need to be in the lab. I need to do the experiment.
Exactly. When I started to Cameroon, I had already the experience of, let's say, a big master thesis, 2 years, where I had been doing some research while teaching. And my conclusion was that what I was loving more than anything else was teaching. So when I left to Cameroon, my plan was to only teach. I went to Cameroon because there was a mandatory military service. Okay, so instead of going to the army, we could go to, these countries just got independent.
Yeah.
There were former French colonies, and it was the first year of independence, and we were going then to help them. We did our best to help them. Okay, I went then to teach, and I got very interested, but teaching only, I realized that I was missing something, and so this is why when I came back, I wanted to do both teaching and doing research. So it was a very good experience for me to realize that this was my life. And all along my life, I have really loved teaching. And as I told you, maybe I would never have found the idea of the switch without teaching the smart students. And I'm not the only one, okay? Albert Fert, another Nobel laureate, French, working in Paris-Saclay, said the same thing. He said, it's because I am a professor, because I was teaching, that I was understanding things better. Because when you have to explain it to the student, you cannot afford to be vague. You have to understand everything very precisely, and it helps you to better understand yourself.
It was actually Einstein who said that if you cannot explain something very, very simply, then that means that you don't really understand it well.
I don't know.
Someone said that. Yeah,
you have to check. I don't know.
I'm going to check that on that. Okay, Professor, I'm just looking at the time, and we probably should wrap up a little bit, but I have a couple of more questions, and usually I have this tradition on the end that I'm ask my guests about predictions on the end. But before we go to it, one last question about Pasqal, actually. So we already mentioned that Pasqal is coming to IPO somewhere this summer. And for you as a founder who are the scientist co-founder, rather than the operator, what that mean for you that the company that you help establish is going to IPO?
I'm just amazed, okay? And I talk about it with Antoine Brouès, and I say, look, Antoine, you realize that you had this experiment in your lab. We were talking of basic physics, and now we go on the New York stock market.
What have you done? What have you done?
Well, you see, so for us, it's fascinating. You know, in my life, I have made many different experiences, okay? Yeah. Not only in physics, but for instance, they asked me to be in the scientific advisory board for President Macron. I go.
Beautiful.
You know, yeah, sure. Plenty of things like that. So for me, it's another experience, discovering what is this situation of a society which becomes public, okay? And I will see.
There's a beautiful variety of experiences, I
Absolutely.
think, that everyone wish.
I love new experiences, and it's really a new one.
Perfect. Okay. Now I would love to ask you about those predictions. And actually, I don't know if this is really a prediction question, but I was wondering, you know, before you start working on the Bell inequalities, and when that was considered to be philosophical and underestimated so much, right? Is there anything like that today that you may think in next, I don't know, 50 years, for example, we look back and we think, oh, that was underestimated so much?
I think that maybe when people try to develop a quantum computer, they underestimate the question that I asked. Is there a fundamental limit to the number of qubits that you can entangle? Maybe if we find that there is such a limit, maybe we will discover that it was not clear. At the moment, most of the people think that it is only a question of technology. But who knows?
Who knows? It's beautiful. Okay. And another question is, if, let's say, a young, brilliant researchers will come to you today and knowing your experience being on this, like, you know, fork of the road, going for standard, well, not really proven, but, you know, like something like safe questions for their PhD thesis or in general the research that they want to perform, or going for something new, maybe risky. Yeah. What would you advise them to?
Oh, well, it's very clear. First, I would ask if the person asks or do not ask a permanent position. And so once a person asks a permanent position, which happens by the age of 30, either in CNRS or at a university, then I would tell the person, okay, you can go your way because you have a permanent position, you will get a salary at the end. You know that it is risky, but it is not enough. You should find a way to convince colleagues that although they think it's a little bit bizarre, in fact, it's interesting. I told you a key point in my case was I was able to convince people that it was interesting. If after 1 year, you have tried many times and never convinced anybody that it is interesting, might be a problem. So this is really my advice. I tell them, okay, if you have an original idea, develop it, but try it on people. And if you cannot convince anybody, it's not a good sign.
Maybe give
because
up.
scientists are more open than people think. In fact, scientists love new ideas. But they
Of course, that's how the science...
Yes, but they want to filter the good ones from the not so good ones.
Yeah. Everyone who's working on something want to believe that this will be successful, right?
Yes,
And
but
able to prove
then you have
something.
to check that you can convince at least a few people.
Yeah. Okay, that's beautiful. Professor, thank you so much. It was a pleasure. Ladies and gentlemen, Professor Aspect. Thank you. That was Blond and Quantum. Thank you for joining me on this journey through the quantum business frontier. If you liked the episode, please review it on Spotify or Apple Podcasts and help more people discover the quantum world without needing to untangle the theoretical physics. See you next time, unless the cat changes the timeline first.